What is nothingness? Is there truly such a thing as nothing? Or is the idea itself a contradiction? And if nothing does exist, what could it possibly resemble? This question has unsettled human thought for centuries, not because it lacks answers, but because every answer seems to collapse under its own weight. The moment we attempt to describe nothingness, we give it form, boundaries, and meaning. In doing so, we unintentionally destroy the very thing we are trying to understand. Both philosophers and physicists have been drawn into this problem, often for the same reason. Nothingness sits at the edge of language, logic, and reality itself. It forces us to confront an uncomfortable possibility, that our universe may be built not only on matter and energy, but on absence, uncertainty, and invisible structure. If you have ever wondered what existed before the universe, what remains when everything is removed, or whether absolute emptiness is even possible, you are already engaging with one of the deepest questions science can ask. In this video, nothingness will not be treated as a poetic metaphor or a philosophical trick. Instead, it will be examined through the lens of modern science. Because in physics, nothing does not mean one single thing. It has several distinct meanings, each grounded in theory, mathematics, and experiment. Here, we will explore 4 fundamental definitions of nothingness in science, and along the way, uncover why emptiness may be far more complex, dynamic, and unsettling than the word itself suggests. Imagine hearing a sound outside your window. You assume it must be a barking dog, or perhaps a child shouting in the distance. But when you stand up and look outside, there is no dog, no child, no obvious source at all. And almost instinctively, you say to yourself, "Oh, there's nothing there." We say this phrase all the time. There's nothing there. There's nothing left. There's nothing. Yet what we usually mean is not true nothingness, but the absence of a specific thing we expected to find. When you look outside, the world is still full of objects: trees, houses, cars, bicycles, shadows, light, motion. The only thing missing is the particular sound you were trying to explain. Even if you were to stare into what appears to be a completely empty room, it would still not be empty. There would be air filling every corner, composed of molecules like oxygen and nitrogen, particles you must inhale just to remain alive. There would be temperature, pressure, electromagnetic radiation, microscopic motion. Emptiness, as we casually use the word, is never truly empty. The universe itself is vast, dynamic, and saturated with matter and energy in countless forms. Everything we see, touch, and interact with is ultimately built from subatomic particles, governed by the same physical laws, all existing within space and time. Galaxies, stars, planets, bodies, thoughts, everything follows these rules. But there is a problem hidden inside this picture. You, I, and everything we call something exist only temporarily. Stars burn out. Particles decay. Even the universe itself appears to have a beginning, and possibly an end, which forces a disturbing question into the open. If everything that exists can cease to exist, how should we think about nothingness? Science does not offer a single answer. Instead, it offers several, and each one challenges intuition in a different way. So when physicists talk about nothing, they are not talking about one idea, but many. And among them, 4 stand out as fundamental. Here are 4 scientific ways of understanding nothingness. Nothingness is the state in which the raw materials necessary for things to exist are absent. If you do not have the building blocks, you cannot have the building. No galaxies, no stars, no planets, no people can exist without the most fundamental ingredients of reality. Everything we have ever observed, touched, or measured is constructed from subatomic particles. In that sense, these particles are not just components of the universe, they are its raw materials. Take hydrogen, the simplest and most abundant element we know. In its ordinary form, a hydrogen atom consists of a single proton and a single electron. This is what we call normal matter, the kind of matter that makes up stars, oceans, bodies, and breath. But physics tells us that this is only half of the story. There exists another version of hydrogen, one that looks identical in mass and structure, yet is made of entirely opposite components. This is antihydrogen. Instead of an electron, it contains a positron, the electron's antiparticle. Instead of a proton, it contains an antiproton. Same shape, same weight, same structure, yet fundamentally reversed. According to the laws of physics as we understand them, the universe should have produced matter and antimatter in equal amounts. Perfect symmetry. Perfect balance. And if that had happened, matter and antimatter would have annihilated each other almost instantly, leaving behind a universe filled with nothing but radiation. No stars, no planets, no life, no observers asking questions. Yet clearly, that is not the universe we inhabit. For reasons we still do not fully understand, normal matter dominates antimatter. This imbalance is what allows galaxies to form, stars to ignite, and the universe to evolve in complex ways. Without it, existence as we know it would be impossible. What makes this even more unsettling is that experiments suggest this asymmetry is not subtle. In 2010, experiments conducted at Fermilab revealed that the imbalance between matter and antimatter may be greater than previously assumed. In the earliest moments of the universe, for every 100 units of antimatter, there were roughly 101 units of matter. That tiny excess, just 1%, was enough to tip the scales of reality itself. That single surviving fraction became everything. This is where the first scientific meaning of nothingness emerges. When people say that matter came from nothing, what they often mean is not absolute emptiness, but a universe that could have easily ended with no stable building blocks at all. A universe where matter failed to gain the slightest advantage over antimatter would have left behind no atoms, no structures, and no complexity. This mysterious process, the origin of matter's dominance over antimatter, is known as baryogenesis. Physicists have proposed many theories to explain it, from subtle violations of symmetry to unknown forces acting in the earliest moments of time. Yet, despite decades of research, there is still no definitive answer. And until that answer is found, one unsettling possibility remains on the table. The universe we see exists only because nothingness almost won. 2. Nothingness is the emptiness of empty space. The first definition of nothingness may not feel fully satisfying. After all, even in that scenario, something still exists. There are particles, forces, asymmetries, raw materials waiting to assemble into structure. That does not quite match our intuitive idea of nothing. So let us go further. To approach a deeper form of nothingness, we must imagine stripping reality down completely. Remove all known matter. No galaxies, no stars, no planets, no living beings. Remove atoms, remove subatomic particles. Erase every object, every piece of mass and energy we normally think of as something. What would remain at the end of this process? If such a removal were even possible, we would be left with what seems like the ultimate candidate for nothingness: empty space itself. A vast, silent expanse with no particles moving through it. For some scientists, this is what nothing means: the void of space, entirely cleared of matter. But here, physics introduces a deeply uncomfortable twist. Even this space is not truly empty. The laws of physics do not vanish just because matter does. And where physical laws exist, so do quantum fields. These fields are fundamental to reality: the electromagnetic field, the gravitational field, the Higgs field, and the fields responsible for the nuclear forces. They do not require particles to be present in order to exist. They are part of the structure of space itself. Even in the absence of matter, space-time remains, governed by general relativity, stretching and curving according to its own internal rules. There is still geometry. There is still structure. There is still a stage, even if the actors have left. And perhaps most disturbingly of all, empty space still possesses energy. At its lowest possible state, space retains what is known as zero-point energy, and this energy is not zero. It has a positive value. Today, this same energy appears to us as dark energy, the mysterious force driving the accelerated expansion of the universe. So even the emptiest space imaginable is not neutral, silent, or inert. It is active, restless, and filled with potential. A universe emerging from nothing, in this sense, does not emerge from absolute absence. It emerges from the hidden content of empty space itself. The laws of physics and the energy embedded within the vacuum seem capable of giving rise to a universe like ours. This, then, is the second scientific meaning of nothingness. Not the absence of space, but the emptiness of space. A void that appears empty, yet secretly contains everything needed for a universe to begin. 3. Nothingness is the lowest energy state possible for space-time. In the previous definition, we touched on the idea of zero-point energy, the energy that remains even when space is stripped of all matter. Despite its name, zero-point energy is not zero at all. It has a positive value. And one of the deepest open questions in modern physics is whether this energy truly represents the universe's most fundamental state. In other words, we do not yet know if the universe is resting at its lowest possible energy level. It is entirely possible that the current state of reality is only a metastable condition, a temporary configuration that could, in principle, drop into an even lower energy state. If that were to happen, the consequences would be catastrophic beyond imagination. A transition to a lower energy vacuum would rewrite the rules of physics instantly. Photons could acquire mass, transforming light itself into a heavy particle. The electromagnetic force, which currently operates over infinite distances, could become a short-range interaction. Light from the sun might no longer be able to reach the Earth. Atoms could fail to hold together. Chemistry, structure, and complexity would collapse at the most fundamental level. Physics allows us to imagine a radically different scenario. A perfectly flat, empty space containing no matter, no radiation, no curvature, and no fluctuations of any kind. A space where energy has reached its absolute minimum, with nowhere left to fall. If such a state exists, it would represent the closest thing to a final physical nothingness. A condition defined as absolute minimum energy, from which no particles can emerge and no energy can be extracted. In this state, creation itself becomes impossible. And yet, even here, nothingness remains incomplete. Because even in this ultimate vacuum, space and time still exist. The framework of physics is still in place. The laws that govern reality have not disappeared. They simply have nothing left to act upon. So this third definition reveals a strange truth. Even the deepest physical version of nothingness is not truly empty. It is a universe reduced to its bare mathematical skeleton, space, time, and laws without content. A nothingness where something essential still stubbornly remains. Nothingness can only emerge when we eliminate the entire universe and the laws that govern it. After the first three definitions, we arrive at the idea of nothingness that most closely matches our everyday intuition. The kind of nothing people usually mean when they say, "There was nothing at all." But to even approach this idea, we must step outside not just the universe, but the very framework that makes thinking possible. Imagine that nothing you can conceive of exists. No galaxies, no stars, no particles. Now go further. Imagine there are no physical laws, no space to contain anything, no time for events to unfold. No before, no after. No structure, no background, no rules. Try to picture a reality where space itself does not exist, and notice how quickly the imagination fails. This is not just difficult, it may be fundamentally impossible. Physicists argue that such a form of nothingness is not a meaningful scientific concept. The moment we attempt to describe it, we unintentionally smuggle something back in. When we say, "There is no space and no time," we still imagine them as missing from somewhere, as if their absence exists within a larger context. But that context itself would already be something. This is why absolute nothingness resists scientific treatment. Science relies on structure, space, time, laws, relationships. Remove all of them, and there is nothing left to measure, describe, or even define. At this point, nothingness crosses a boundary. What we are describing is no longer a physical state, but a philosophical idea. A concept that can be discussed, questioned, and debated, but not tested, modeled, or observed. It exists not in equations or experiments, but in thought itself. And perhaps that is the final irony of nothingness. The moment it becomes complete, it becomes unreachable. Among these 4 definitions of nothingness, you may find yourself instinctively drawn to one of them, thinking, this must be what nothing truly is. And yet every choice comes at a cost. Each definition leaves us face to face with questions that refuse to stay silent. If there is no space to define position, and no time to define moments, how could space-time itself ever come into existence? If space does not exist, how can we even imagine something being outside the universe? If time does not exist, in what sense could anything have a beginning? And perhaps most disturbingly, how could the laws of physics emerge from a state where absolutely nothing exists? These questions are not flaws in our understanding. They are the natural consequences of pushing human thought to its limits. In that sense, all 4 definitions are valid, each within its own domain. Physics, cosmology, and philosophy are not contradicting one another here. They are approaching the same mystery from different angles, using different tools. The real challenge is not deciding which definition is correct. It is recognizing which kind of nothingness is being discussed at any given moment. Because when we fail to make that distinction, we do not just misunderstand nothingness, we misunderstand the universe itself.